Hydrogen fuel. What is it? How is it used? And how can it help us move towards a zero carbon future? In another episode, we discussed potential pathways to reaching a net zero America by 2050. Hydrogen is mentioned in this report as a means to store energy without relying heavily on batteries. But what does that mean? In this episode, we are going to provide a deeper insight into hydrogen, how it is made, how it is used, some of the latest advancements along with current constraints to this technology. So what's so special about hydrogen? Well, hydrogen can be used not only as energy, but also as feedstock and a means to store energy. In this diagram, we see that hydrogen can be used to power vehicles, create fertilizer, and process metals like iron and steel. Another added benefit of hydrogen technology is that it can, in theory, be used to power sectors of the economy that are harder to electrify, such as long-haul shipping, aviation, and various industrial processes. But why hydrogen? Hydrogen is the most abundant element in the universe. However, on Earth, it is not naturally found all by itself. Here in this model, you can see that it is usually attached to other elements such as oxygen, which creates water, or carbon, to create hydrocarbons like methane. Because hydrogen does not exist alone in nature, it needs to be extracted. This pie chart produced by the International Energy Agency tells us that currently 99% of the hydrogen we extract is a byproduct of fossil fuels, natural gas, and coal. To distinguish each source of hydrogen production, scientists use a color classification system: brown, gray, blue, and green. Hydrogen derived from coal is known as brown hydrogen and is produced via a process known as gasification. Gray hydrogen, which accounts for about 80% of the world's hydrogen production, is produced via steam methane reformation and is derived from natural gas and fossil fuels. Both brown and gray hydrogen release CO2 as byproducts, thus contributing further to climate change impacts. However, blue hydrogen involves the capture and storage of this CO2 byproduct. But if the aim is to remove harmful greenhouse gases from the atmosphere, clean hydrogen fuel cannot be created through fossil fuel burning. In the effort to eliminate fossil fuels, green hydrogen takes all of this a step further via a process known as electrolysis, also known as water splitting. Here, an electrolyzer splits freshwater particles into hydrogen and oxygen using an electric current. If renewable energy like wind or solar is used as the electricity source, then the derived hydrogen is known as green hydrogen. Another form of green hydrogen involves biomass gasification. This involves growing high-energy plants and then converting them at more than 700 degrees Celsius temperatures to hydrogen, carbon monoxide, and carbon dioxide. Although this method does produce some carbon dioxide because the plant absorbs carbon dioxide while it is being grown, it results in lower carbon emissions in comparison to brown and gray hydrogen. So now that we know the various means by which hydrogen is produced, let's talk about how hydrogen can be converted into electricity using fuel cells and the pros and the cons of those processes. Due to the fact that hydrogen itself can only store energy, it must be processed through a fuel cell in order to be used for power. At the core of this technology, we see that hydrogen and oxygen atoms are bonded to produce energy and water as a byproduct. When we take a look inside a fuel cell, we see that we have an input of hydrogen on the cathode side and an input of oxygen on the anode side. A catalyst is used to split hydrogen into its electrons and protons. The cathode is what holds onto and attracts the hydrogen electrons, while the protons pass through a membrane as they are attracted to the anode where the oxygen is. Then, the electrons are pushed through a circuit to produce an electric current and heat. The hydrogen electrons are then reunited with the protons and with oxygen to form water. Cells like this can then be stacked and used as a source of energy inside vehicles or as power for energy plants. But what do we do with hydrogen when we don't need it quite yet? The most expensive option is to store it in pressurized tanks. It can even be liquefied and stored in cryogenic tanks. But what you probably didn't know is that we can also take hydrogen and store it underground in salt caverns. This method has been proven to be safe and reliable, considering it doesn't require high pressurization, and it's also the cheapest way to store hydrogen for long periods of time. However, using hydrogen as a fuel source comes with several disadvantages. Freshwater is a limited resource. Can we afford to use our freshwater resources for electrolysis to produce hydrogen? The process from extracting hydrogen, transporting it, and consuming it is highly inefficient. Between extraction and consumption, around 70% of energy is lost. The main reason why hydrogen remains a relatively feasible alternative to fossil fuels is because it is energy dense. This means that it can store a lot of energy in a small volume. Additionally, hydrogen is a highly flammable and odorless gas. Should a leak go undetected in a potentially explosive environment, the results could be disastrous. When it comes to biomass gasification, this process still results in greenhouse gases like carbon dioxide and carbon monoxide. We also do not currently have enough infrastructure, such as fueling stations or pipelines, to distribute hydrogen across the country. And lastly, it's simply still not economical at this time. Using hydrogen only makes sense at scale, and it still needs more financial support to get there. What makes things even more complicated is that the cost of replacing fossil fuels for hydrogen is highly dependent on who's producing it and where. Regional variations in hydrogen production costs depend on factors such as prices for fossil fuels, electricity, and carbon. In fact, according to a report released by the International Energy Agency in 2019, natural gas without carbon capture and storage is currently the most economic option for hydrogen production in most parts of the world, with costs being as low as $1 per kilogram of hydrogen in the Middle East. In this chart, we see that the most expensive option globally is green hydrogen, ranging from $3 to $7.5 per kilogram. However, green hydrogen may be more attractive in regions that already rely heavily on renewable resources or nuclear power plants, especially if their current import costs of natural gas are relatively high. Though this isn't to say that investments aren't being made to lower the cost of hydrogen fuel, governments and universities around the world are investing more and more into making hydrogen as efficient as possible. In May 2020, Ben Wiley, a professor of chemistry at Duke University, and his colleagues published a study that demonstrates the potential of using nickel microwire mesh as a more productive electrode in the water splitting process. A more productive electrode means lower overall cost of electrolysis. Let's hear from Ben on how they were able to make this possible.
If you try to run this thing really hard, pretty soon your anode or cathode, one or the other, is going to be covered with gas, and you won't be able to pass any more electricity through it. And so we thought, well, how about you run flow over the electrode, like fluid flow, to drive the gas off? And then you can imagine, okay, a metal plate is good, but what if I make the surface area of that metal plate, way bigger? And so by splitting it into tiny nanowires. And so you can imagine taking like a piece of steel wool, like that's going to have a lot more surface area than a piece of steel, right? So, and that means if it has more surface area, there's more surface area to pass electricity to the oxygen or hydrogen atoms in the water. We looked at 3 different length scales of these kind of porous materials made of nickel in this case, since nickel is pretty good for water splitting. We used like a nickel foam, a nickel microwire mesh, and a nickel nanowire mesh or felt. And we thought the nanowire felt would be the best because it has the highest surface area, but it wasn't. It was very tight and trapped the bubbles from water splitting. So it was the microwire mesh that we could flow the bubbles out. So that ended up being the best electrode.
As it stands today, the cheapest way to make industrial quantities of hydrogen is through steam methane reformation, where methane is broken down using very hot steam. Based on Wiley's results, by improving the materials used to make electrolyzers, water splitting can become a viable alternative to producing massive amounts of hydrogen, thanks to higher production rates, meaning lower costs. But what about lithium-ion batteries? Why even bother with hydrogen when we can use batteries to electrify our vehicles and store energy? Well, the answers are fairly simple.
For long durations of storage, it makes a lot more sense to store the energy in hydrogen because you can just store it in a big steel tank rather than in a gigantic battery. And then you can run your fuel cell off that stored hydrogen for a very long time. Whereas batteries, they'll typically discharge them in a matter of hours.
Another added benefit is that vehicles powered by hydrogen are capable of being refueled at much faster rates than electric cars. An average electric car can take between 45 minutes to several hours to fully refuel. Hydrogen cars, on the other hand, can be refueled within 5 minutes. What's even better is that you can go longer distances on hydrogen fuel. It's lightweight and it takes up considerably less space than a battery would. This makes hydrogen particularly attractive for long-haul shipping and aviation. In fact, the larger the vehicle, the more sense hydrogen makes cost and energy use-wise. When no country today can produce green hydrogen on a large scale, many are making steps to make this future a reality. According to this map pulled from the 2020 report by the World Energy Council Germany, 42 countries are currently moving in a direction to create national strategies to support green hydrogen production, while 9 countries are already there. By 2025, it is expected that these strategies will likely cover countries representing over 80% of global GDP. So, from a policy perspective, green hydrogen is well on its way to play a significant role in electrifying our future and going net zero by 2050. Moving forward, it will be important to keep an eye on how advances in technology continue to lower costs for this energy sector, how policy supports this transition, and how fast infrastructure can be built or converted to support hydrogen expansion. Check out our full-length podcast with Ben Wiley, where we go into further detail about the current state of hydrogen technology, or check out our newsletter. To sign up for new releases and more, visit climatenow.com. Thanks and see you next time.